So, welcome to this session, which is essentially the continuation of the discussion of the alternate mode sets, which are going to be subsequently used for the analysis of the partially filled rectangular waveguide. So, the alternate T to x and T m to x relevant mode sets which are pertinent to this particular problem at hand. Let us go to the lecture slides. Now, for the rectangular waveguide which is given here, the boundary conditions on the problem would mean that the tangential components of the electric field will vanish at the conducting walls. That means, E z must be equal to 0 at x equal to 0, x equal to a, y equal to 0 and y equal to b. Similarly, E x must be 0 at y equal to 0 and y equal to b, and E y must be 0 at x equal to 0 and x equal to a. So, this must be satisfied by the mode functions for the rectangular waveguide. So, let us call this equation 6, which define the boundary conditions that needs to be satisfied by the mode functions, the T to x and T m to x modes in the rectangular waveguide or in the homogeneous rectangular waveguide, the rectangular waveguide filled up with a homogeneous material. So, therefore, in order for these boundary conditions to be satisfied for modes that are T m to x, the psi function for the T m to x mode will be cos the psi function for the T m to x mode will be cos m pi x by a sin n pi y by b e to the power minus j k z z. Okay. Because at y equal to 0 and y equal to b, the E x has to vanish that is dictating sin n pi y by b, and at x equal to 0 and x equal to a, the E y has to be 0. Because at y equal to 0 and y equal to b, E x has to be 0. So, which is determining this component, and at because at y equal to 0 and y equal to b, E x has to be 0, which is determining this component, and at x equal to 0 and x equal to a, E y has to be 0, which is determining this component. So, in this case m can take the values of 0, 1 and 2, etc. So, in this case m can take the values of 0, 1, 2, etc., and n can take the values of 1, 2, 3, etc. And k z is given by beta, that is equal to k root 1 minus f c by f whole square for f greater than f c for f greater than f c, where f c is the cutoff frequency, and k z equal to minus j alpha and k z equal to minus j alpha equal to k root of 1 minus f by f c whole square for f less than f c. F c for the m nth mode, or the cutoff frequency for the m nth mode, is given by k c by twice pi root of epsilon mu. K z is given by beta, that is k root of 1 minus f c by f whole square for f greater than f c, where f c is the cutoff frequency, and k z is given by minus j alpha, that is equal to k c root of 1 minus f by f c whole square for f less than f c. Where f c m n, the cutoff frequency of the m nth mode, is given by k c by twice pi root of epsilon mu, and that is equal to 1 by 2 root epsilon mu root of m by a whole square plus n by b whole square. So, let us call this equation 8. And in this case, m is given by now for the T to x modes, or we can also say T to x m n modes, the corresponding psi function for the T to x m n mode is given by sin m pi x by a cos n pi y by b e to the power minus j k z z. Let us call this equation 8, where m is given by 1, 2, 3 etcetera, and n is given by 0, 1, 2 etcetera, and k z is as given before. The value of k z is the value given before. So, again we see that the boundary conditions have to be satisfied by the choice of the appropriate psi function along the x and y direction. Namely, the E x has to be 0 at y equal to 0 and y equal to b, and E y has to be 0 at x equal to 0 and x equal to a, which will determine these two field distributions or these two potential function distributions. So, that when we calculate E x from here, it has to vanish at y equal to 0 and y equal to b, and when we calculate E y from here, it has to be 0 at x equal to 0 and x equal to a. So, that will determine the choice of these two potential functions. This is similar to the rectangular waveguide which we studied earlier. So, now from 3, if we look at equation 3, The characteristic impedance of the TM to X modes the characteristic impedance of the TM to X modes can be calculated. So, we have can say that for the computation of the characteristic impedance of the TM to X modes, we can use equation 3 to find out E x as 1 by j omega epsilon del square del x square plus k square psi m n T m x and that is given by 1 by j omega epsilon del square del x square plus k square. Just substitute. So, cos m pi x by a sin n pi y by b e to the power minus j k z z. So, that is 1 by j omega epsilon k square minus m pi by a whole square psi, because of the del x square operation we have minus m pi by a whole square when we perform the derivative del x square on this function. So, it becomes k square minus m pi by a whole square psi. So, that is equation 9. Then from equation 2 we can find h y as del psi del z, that is minus j k z that is minus j k z psi. Let us call this equation 10. So, therefore, the z directed wave impedances are Z0 Mn for the Tm to x mode as Ex by Hy, that is k square minus m pi by a whole square divided by omega epsilon k z, and that is equal to k square minus m pi by a whole square by omega epsilon beta for f greater than f c, which is the cutoff frequency, f c being the cutoff frequency, and that is equal to k square minus m pi by a whole square by minus j omega epsilon alpha for f less than f c. So, this is equation 11. Then for the characteristic impedances of the T to X modes, for the characteristic impedance of the T to X modes, we obtain from equation 4 E y equal to minus del psi m n T to X del z that is equal to j k z sin m pi x by a cos n pi y by b e to the power minus j k z z, that is equal to j k z psi. This is equation 12. Similarly, from equation 5, we obtain h x as 1 by j omega mu del square del x square plus k square psi m n T E x, that is 1 by j omega mu del square del x square plus k square sin m pi x by a cos n pi y by b e to the power minus j k z z, and that becomes equal to 1 by j omega mu and that becomes equal to 1 by j omega mu k square minus k square minus m pi by a whole square times psi. We call that equation 13. And therefore, the z directed wave impedance becomes z0 becomes z0 mn t to x as minus E y by h x, that is omega mu k z by k square minus m pi by a whole square. So, this can be written as z0 mn t to x as omega mu beta divided by k square minus m pi by a whole square for f greater than the cutoff frequency f c, or the frequency greater than the cutoff frequency f c, and that is equal to minus j omega mu alpha by k square minus m pi by a whole square for the frequency less than the cutoff frequency f c. So, let us call this equation 14. So, that ends the preliminary framework we need for the mode functions of the T to x and the Tm to x modes, which we are going to now use to analyze and find the dispersion characteristics of the partially filled rectangular waveguide. So, this is where these kinds of mode functions or alternate mode functions are going to be used to satisfy the new boundary condition or the additional boundary condition which is present at the dielectric air interface inside the partially filled rectangular waveguide. So, this will be continued in the next session. Thank you.